Welcome back. This next video is going to be on the rank of a matrix. The rank of a matrix is defined as the number of linearly independent rows or columns of the matrix. So the largest that a rank can be is the smallest of the number of rows or the number of columns. So for example, if we had matrix A and it had the values 3, 1, 6 going down 2, 4, 2. We see that the rows equal 3 and the columns equal 2. Well, like I said, the largest that a rank could be is the smallest of the number of rows or the number of columns. In this case, the rank, which equals R, would be 2 because that's the smallest number of columns. If one or more rows can be written as a linear combination of another row or rows, then the matrix is not full of rank, and it is called singular. Now we mentioned before that if this is a square matrix and it's singular, there is no inverse. We mentioned that in matrix inversion. So for instance, if the third column of a matrix can be written as the first column multiplied by a constant, then the matrix is not a full rank. So I'll demonstrate that with matrix B here. So let's have the same values, 3, 1, 6, 2, 4, 2 going down, but let's add another column, 6, 2, and 12. Okay, what is the rank? Well, the rank is 2 because if you look here, the first column times the second column, or excuse me, first column times 2 is 6. So 1 times 2 is 2, and then 6 times 2 is 12. So I guess what I should have said is that the third column of this matrix can be written as the first column multiplied by a constant. And because that there is such a linear combination, our rank is just 2. Because you can get the third one from the first one. Now, let's take a matrix C with the values 3, 1, 6, 2, 4, 2 going down, and then this time let's change the third column to be 5, 5, 8. What is the rank of this one? Right, this one is also 2 because you can add the first column and the second column to get the third column. 3 plus 2 equals 5, 1 plus 4 equals 5, 6 plus 2 equals 8. So that's another linear combination. And we can say if this was full of rank, it would be rank 3 because the smallest number of rows or columns is 3. However, because the third column is a linear combination, the rank goes down by 1. So for a square matrix, if the determinant is 0, then the matrix is not full of rank. Now, we mentioned also before, talking about matrix inversion, if the determinant is 0, then the matrix is singular, therefore there is no inverse, just as a side note there. So let's do D. Okay, in D we'll have 3, 2, 6, and 4. It's a 2 by 2 square matrix, and we can find the determinant of D to be 3 times 4 minus 6 times 2, which is 12 minus 12, which is 0. So because the determinant of D is 0, we can say that D is singular, and there is also no inverse. a matrix that is full of rank is also called a non-singular matrix. So let's take, since we're going according to the alphabet, let's do E here. E will have 3, 1, 6, 2, 4, 2. And then let's do 7, 0, 3 as the third column. And the rank of this one is equal to 3. In this case, a third column or any of the columns is not a linear combination of the other columns. So because this is full of rank, it is non-singular. So a matrix of rank R can be represented as vectors in R-dimensional space. So in this case, E is rank 3, and it can be represented as vectors in 3-dimensional space. Okay, now a matrix is positive definite if each of its upper left submatrices has a positive determinant. So for this one, to demonstrate this, we can use B or C or E. Let's use E. So we're going to take the upper left submatrix, which the only one we have here is this one. Now just as a side note, let's say we had a large matrix. And what we mean by upper left submatrices are these. So we can say this is 1, 2, 3, 4, 5. So like a 5 by 5 matrix. This would be upper left submatrix. This one would be as well, and this one. So a matrix, once again, is positive definite if each of its upper left submatrices has a positive determinant. So let's get the determinant of this one. The determinant of 3, 2, 1, 4 is equal to, we have 3 times 4 is 12, minus 2 times 1 is 2, which equals 10. So because this has a positive determinant, we can also call E positive definite. Now in order for this to hold, it is clear that the positive definite matrix must also be of full rank, since the determinant of the matrix must be positive. And we can see here that it is full rank. Rank would equal 2 here. A positive definite matrix is somewhat similar to a positive real number. It's very analogous to that. So for example, in the section where we talked about calculating the triangular square root of a matrix using the Cholesky method, that matrix was designated as a positive definite matrix. And just for recall, we used a matrix A that had the values going across from left to right: 4, 6, 2, 6, 16, 3, 2, 3, 9. You see that? Okay. And we can see here the upper left submatrix would be 4, 6, 6, 16, and the determinant of that we found to be, this is 16 times 4, 64, minus 6 times 6, 36, which equals 28. So that is a, that matrix is positive definite as well. So this is similar to requiring a non-negative number when taking a square root in order to get a real value. So if we looked at the square root of -2, well, we can't do that. We have to have a positive value in here. Same thing goes for this definition in order to be a positive definite matrix. So lastly, a matrix is positive semi-definite if each of its upper left submatrices has a non-negative determinant. So non-negative, it could be positive, like E here is, and this A matrix, or it could be 0, as we got here with D. So lastly, let's take a matrix F, and let's give it the values 3, 6, 6, 2, 4, 2, going down, 7, 0, 3. So we're going to take the upper left submatrix, and let's find the determinant, 3, 2, 6, 4. So it's going to be 12 minus 12, which equals 0. So because this is non-negative, we can say that this is positive semi definite. Same thing goes for E and D and A as well. Alright, any questions? Alright, that's about rank of a matrix, some definitions for you there. Hope you had a good time.